Hi everyone, let's talk about molar mass, which as the definition says, is the mass in grams of a mole of a substance. So the mass in grams of 1 mole of a substance, you gotta understand that's referring to this many particles because mole is a number. Just like the word pair represents a specific number, just like the word dozen represents a specific number, the word mole represents a specific number, and if no matter what it is, a mole of anything, whatever its mass is, that's the molar mass. So another thing to consider is that different atoms have different masses. So large atoms such as mercury are going to have a different molar mass than smaller atoms such as sulfur. And it's actually pretty much unique to each atom. I say pretty much because different isotopes can result in some overlap. For the most part, each element has its own unique molar mass. Now, there's no need to memorize it. It's right there on your periodic table. And you'll find, like if you zoom in on the periodic table, this information, which will include a small number, which is the atomic number, that's the number of protons in that element, and the larger number, which is not only representing the number of protons and neutrons added together, but it also tells you the number of the mass in grams of 1 mole of the substance. So what's shown here is that 1 mole of iron has a mass of 55.845 grams. That is something, again, that doesn't need to be memorized. It's here on the periodic table, and that can be applied to various other elements as well, such as these. Now, a note about how we're going to handle it in this class right here, round no further than the hundredths place. Why do I say that? Reason why is because while in this particular example, the mass of iron here agrees with the mass of iron here on this periodic table, that's not always the case. Sometimes two periodic tables will give you slightly different numbers. So because of that, what we're going to have people do is take whatever the periodic table says and round no further than the hundredths place. That means for hydrogen, instead of the 1.00794 grams per mole that's on this particular periodic table, we want that you go no further than the hundredths place. That way, no matter what periodic table you use, you're going to get the same number. Is this correct? Technically not really. You're losing accuracy. But with that said, we do it because it makes it easier on us teachers, because we know that if students are doing it right, they're going to get the same answer. And it makes it easy for students because this way, no matter what periodic table they use, if they did it right, their answers will match the key. So that's why we're going to have people go no further than the hundredths place. So what that means is like, okay, this is the hundredths place right here. That 0 is next to a 7, so it turns into a 1. That's why it's 1.01 grams per mole. So that's the idea of rounding no further than the hundredths place. Nitrogen, we round to the hundredths because it goes beyond that on here. Argon, it goes beyond hundredths place, we round to the hundredths. Mercury, it goes exactly to the hundredths on here, so we round, just write it as is. Calcium goes beyond the hundredths, so we round. Now, I say no further than the hundredths place because lead is written on here as 207.2 grams per mole. That's the tenths place. So the hundredths place is not a goal, it is a limit. What that means is if it goes beyond hundredths place, round it back to the hundredths place. If it doesn't reach the hundredths place, then write whatever you have. So in this case, if it gives lead to the tenths place, you just write lead round to the tenths place. Or if you have something round to the nearest whole number, such as francium, mass of 223 even, you just write it as 223 even. So with that in mind, let's talk about now how instead of individual elements, like pure elements, how would you handle something that is a molecule or a compound? An example of something that's a molecule but not a compound is hydrogen, because it's a diatomic element. So that would involve taking that mass of one hydrogen, which again, you get that off the periodic table, rounded to the hundredths place, and adding two of them together. This represents adding two of them together. And for sig fig rounding, we haven't changed any rules. If you're adding two of them together, addition rules say round to the same decimal place. So hundredths place, hundredths place. Or even for larger elements, it'd be the same thing. So this is 2 hydrogens added together, 6 carbons. There's your 6 carbons right there, rounded to hundredths place. There's your 12 hydrogens, rounded to the hundredths place. There's your 6 oxygens, rounded to the hundredths place. And when you add them all together, you're taking 6 of these plus 12 of these plus 6 of these. So in other words, hundredths place, hundredths place, hundredths place is going to mean you need to stay rounded to the hundredths place. Because when you add or subtract, you count decimal places, not number of sig figs. So that's the reason why that's rounded the way it is. again, hundredths place is the limit, not the goal, with that in mind, but so far all of these just go to the hundredths place. Now, other compounds such as methane, you're going to be following the same rules. If methane is 1 mole, methane contains 1 mole of carbon and 4 moles of hydrogen. Likewise, the process will involve adding up 1 molar mass of carbon plus 4 molar masses of hydrogen. And when you add them, look, it's still the same thing, hundredths place, hundredths place, hundredths place. Now here's other compounds that's been the same deal, okay? 2 hydrogens, 1 oxygen, 4 hydrogens, 1 oxygen, 1 carbon, or 1 calcium, 2 nitrogens, and 6 oxygens. Add them all together, or I should say we'll add for the water, or add for the methanol, or add for the calcium nitrate, and we leave it round to the hundredths place in each of these particular cases. Same for oxygen gas, hundredths place, hundredths place. Now, watching an answer and recognize it's correct is one thing. It's quite another to actually be able to produce a correct answer. And when a student has a downfall on a test, it's usually something like that. So this is a good time to practice, to pause and practice. Now, of course, I won't leave you hanging. I'll show you how to get the answers for these, but this is a good time to pause and practice and then check to see if you did it right. So, carbon dioxide. You should know that that's CO2. And since CO2 is the formula, 1 carbon, 2 oxygens should add up to that. Bromine. There should be awareness that this is Br2. And 2 bromines added together, your calculator will spit out 159.8, but since it's hundredths place, you need to end at hundredths place. So add a 0. Don't just take the calculator's word for it. Helium. You should know that helium is not a diatomic element, it's a noble gas, so it's just 1 helium. So the molar mass is 1 helium. Lead 2 sulfide, which, by the way, the formula for that is PbS. That's the mass of 1 lead plus 1 sulfur, which means you are taking 1 lead plus 1 sulfur. Notice the rounding, because this one stops at the tenths place, so you're limited to the tenths place because it's a less accurate number than this one. So this one limits you here. Oh, get this out of the way. Now for these last couple, I have put the answer but not the work, because the person completing these notes should do all of the work. Don't skip the work. Show how you added it all up. But at the end of it, you should look at your final answer and see that it matches this or that. All right. Now with those things being mentioned, this is the list of what's on the quiz over this note, so make sure that you're familiar with all these things. This is also available on the website where we posted the notes, and so you can check there if wishing to see a higher definition version. But again, this is the stuff to know. All right, that's it.